ML, but I'll still try to explain most of the thing. And if you have some questions, I think we'll make a short Q&A session in the end. Most of the things I tell you we are doing in Alfa-Bank, some of them are already, exactly to say, most of them are already in production and some in development now. Okay, the agenda is to speak about client communication journey with the bank, how client communicate with the bank via different channels, via chats, chatbots, voice bots, and how classical approaches with classical NLP models transform to generative approach. As you know, nowadays everyone is doing something with large language models. And I'll give a talk about how we use large language models in practice, how they allows us to make better client experience, and some tips how to use LLM in real life tasks. So let's start with the sources. As you know, natural language processing is working with texts. And of course, the main source of text in bank is dialogues. There is a mobile application. There is a chat where a client can ask his questions, ask to do something. And there is a chatbot and human operator. Less obvious source is voice communications. Still we have automated speech recognition, speech to text. We can treat voice communication as source of text also. And there are plenty of other text sources, documentation, code, news, media monitoring, and so on. So let's start with chatbot. Imagine we live in pre-ChatGPT era, before the hype around LLMs. So, and our task is to build a dialogue system. What can we do? The first and the most simple, straightforward approach is to just write down the possible answers for all questions and do classification. We have client question, for example, client asks us about his transaction limits. Then we classify his intention, so-called intents, what client wants, basically. And for each intent, we have a set of predefined, already written by humans, answers. So this approach is called something like rule-based or scenario-based approach. The client moves along predefined path, like on railway, and for every message we detect the intent, what client wants. For example, he wants check transaction limits, and for this intent we have predefined answer to check transaction limits, follow steps, etc., etc., and we show this answer to client. So what does a classic non-generative pipeline look in this case? The classic NLP pipeline is like this. We take Bert, something like Roberta. We collect a huge data set of unlabeled dialogues. Because the dialogues are unlabeled, we are not limited in the size of data. We do pre-train stage using masked language modeling when we mask 15% of tokens at the high level in the text and train the model to predict them. After this step, we assume that model has some understanding of language about our domain, and then we do fine-tuning stage. For this stage, we need to collect a supervised data set. Basically, it is a labeled data set of pairs where we have client question, and we have a class for this question, the corresponding intent. And we do text classification tuning for our BERT. Optionally, we can do distillation to make the model smaller, to make it faster, because in practice, when you do such classification, you can receive dozens, hundreds, in some cases, in some bindings, maybe thousands of requests per second. It means that your BERT should classify intents dozens and hundreds times per second. So you want it to be fast. And that's why you can do distillation. You can take a smaller model and train it using the bigger one. Okay, let's move on to the inference stage. We have client question, we have our BERT, and we have probability distribution over all classes. For each class, we have some score, like probability. And we take the top score, the maximum score, and we have a set of thresholds for every class. And we say, if the top score is lower than threshold, then our model is not sure, and we can't say what client intent is. We need a human operator to transfer the dialogue. So this is the place where two key business metrics appears. First is client satisfaction, client feedback. It's basically how satisfied clients are with chatbot. And the second one is percentage of automated dialogues. How often do we transfer the dialogue to the operator? And there is a clear trade-off. We can take our thresholds, we can raise them, then our answer relevancy will go up because we answer only in those cases where classifier is sure. And at the same time, number of undefined intents also goes up, leading to better client feedback, but worse percentage of automated dialogues, and vice versa. We can change all arrows in this scheme, and it will be correct. So this approach is simple, and that's why it has plenty of disadvantages. The first is number of intents. In practice, this number of intents is finite. We have approximately 400, 500 of intents. Some other banks in Russia, I know, have maximum 1,000 of intents, but it's still small amount. And we can be sure that for all possible cases, for all possible questions, we have corresponding intent. And we are falling in new intent problem. For example, there is some new product, and users start asking about this product in chatbot, and there is no such intent. Our classifier just can't predict such intent, and the chatbot just can't answer for those new questions. The simple, straightforward solution is, okay, just update the train set every time when something new happens, when new intent appears. This is simple approach, but it requires regular support in practice. And there is more advanced solution. You can train an embedding model. Embedding model is model that return a vector. And you do create embeddings for intents and for queries. And you just find the nearest intent to client query. Those embedding models are usually trained like sentence transformers. Sentence transformers are transformers, usually transformers encoders, but they are trained not like BERT on mask language modeling. They are trained using contrastive learning approach when you try to put semantically similar sentences closer together in the vector space and dissimilar questions further apart. In practice, we are using naive solution. We can afford to hold a team of data labelers, of human assessors, and we can regularly update our train set and retrain model if needed or by the schedule. But some other banks in Russia, I know, using the second one approach with embedding models, and it's quite cheaper when you speak about new intents. The second problem is complex queries. This approach works really bad when your client question is complex. For example, a client might ask something that requires reasoning, doing small computation, or client can ask a question that consists of sub-questions, And sometimes those sub-questions can be unrelated at all. And of course, there is some workarounds. We can try to do segmentation to subqueries and do separate classification or some other things, but still it's just workaround. And this rule-based approach is bad when we speak about complex questions. Next thing is regular support. As I already said, we need to collect new label data every time. We need to retrain model every time. The solution sounds simple. Okay, let's do automation. Let's create train pipelines that work automatically without humans, without data scientists. It sounds easy, but in practice, that's not so easy. But we've almost done this. Next problem is answers. They are written by human, they are fixed, they are constant, and they are not adaptive. For example, we can imagine a case when a client asks two almost the same questions, but with different style, with different words, and the answers will be the same for both of those questions. So possible solution is we can try to write down multiple answers per one intent and do vector-based search for the most relevant. So we classify the intent first, and then we do vector search for the most appropriate, the most corresponding answer using embeddings. But that's also just workaround. It's not solving the problem in the whole. The next thing is operator. Operator is required if we don't know what intent the message belongs to. And the good idea is to create a hierarchical classification when we group some class, when we group some intents into higher level groups. And those groups are called pools, and we do this higher level classification. For example, if client asks us about something about credit card, we don't know exactly what does he want, but we can classify that this is pool credit card, and we can answer him with a predefined answer. For example, we can ask him what exactly does he want about credit cards. And final drawback is context. By context, I mean dialogue history. In practice, there is often no access to dialogue history. So the classifier works only based on the last message from the client. And it's easy to understand that that is not a good strategy. Some clients may split their messages into several short parts. For example, I like to do so. And our intent classifier fails in those cases. So solution seems obvious. Okay, let's do intent classification based on dialogue history and the query. In practice, when we speak about banking, when we speak about complex infrastructure, a lot of different systems working together, it is technically a hard problem to do such simple thing as classification based on the dialogue history. We have done it, but I know big banks in Russia, almost IT companies that still haven't solved this. And their chatbots are working only on the last message you type. So these are the main limitations of the classic approach. This approach has been widely used since 2018, 2022, and remained the standard up until 2022, 2023. But then ChatGPT movement happened. I'm sure you've all heard about ChatGPT, Llama, DeepSeek. Maybe someone heard about Gemini, Gamma from Google, Mistral, Claude, and so on. These are really great tools. This model changed the game. They are generative, they are context aware, they are far more flexible than just BERT classifier. So, of course, we would like to use such powerful tools to solve our problems. Let's take a step back and look at those problems list. Does an LLM solve the problem of new intents? In practice, not really, because out of the box, LLM doesn't know anything about new products, for example. But LLM for sure handle complex queries much better. They are trained to work with complex questions. They even do some reasoning. They can do some simple calculations and so on. LLMs don't need to be retrained every time. In practice, we almost do not need to label some data for them, but some support actually needed, but in different sense. Answers from LLM are not fixed. They are exactly adaptive. LLM can adapt the answers for your client questions. You still need an operator because LLM still can answer to some questions. And if we solve the problem about dialogue context access, LLM are designed to work in dialogue. They understand context. And if you manage to properly pass the dialogue history to the LLM, it will take it into account. So let's move to the core part of the talk, is adding LLM to the current classification pipeline. We have two options. The first option is, okay, let's take whole systems that were developed for all these years, put it aside and take a large language model and ask it to solve all client problems. Of course, this approach is very risky and hard in practice. We can lose client satisfaction and client trust immediately. So the most optimal path is the second one, is to merge current item-based pipeline with LLM. We still can use huge labeled data set we've collected through all this time. All the corner cases are already considered in these scenarios, in these scripts, in this role-based chatbot, so we also keep them. But we can add some generative parts so to make client experience better. We can treat LLM as a fallback mechanism. So what happens in the pipeline? Imagine we have intent classification and it fails. So it means that the class distribution is too flat, almost uniform, and the model is not sure what is client intent. We don't know how to answer. Imagine our intent pool classification also fails, those higher level groups. We don't know what group it is. This is the point where LLM can help us, where we can integrate them. The first idea is to use LLM for directly intent classification. We can just take LLM, take prompt, and put in this prompt client question, and add dialog context, dialog history, and output from our classifiers. We can take top K predicted classes with corresponding scores and intent descriptions. We can take example questions and do the same for intent pool classification. Put all this into prompt and ask LLM something like, could you please predict the client intent? This approach, called in-context learning, we do not fine-tune LLM, we just prompting LLM. The next approach is called instruction tuning approach. Let's briefly recall on the conceptual ideal level the typical stages of training a large language model. First, there is pre-training stage, when we just train the model to do next token prediction problem. So after that stage, LLM is basically just text continuation engine. For example, if you prompt it with some question, the most probable output you'll get is another question, because LLM just continues the most probable generation. But in practice, we know that LLM actually answers our questions. This is happening on the second stage when we do instruction tuning, when we pass some instructions and we do self-supervised tuning, supervised tuning, pass some instructions, put input and show the output we want to see from the LLM, and we just do supervised tuning on such samples. This data set for instruction tuning is much smaller. We need much less compute. For example, in pre-train stage, we need a lot of data, a lot of compute. And next goes RLHF stage, reinforcement learning from human feedback. I think other speakers will go deeper in those phases. But what can we do for our case? In our case, we can do instruction tuning just on one instruction. We can ask model to classify user intent, give it context, give it maybe predictions of our basic classifiers, intent classifiers, and pool classifiers, and just train it to output the true intent. The third approach is to use LLM as an embedder. As you all know, large language models are just transformer decoders, basically, with a lot of blocks. And as an input, it takes some text, do token splitting. Then for each token, we have input token vectors. We pass that through all decoder blocks, and we receive output token vectors. After that, usually goes some classifier, some head, which predicts the most possible token. But we put that head aside. We just take last hidden state, create somehow an embedding of the whole sequence, of the whole sentence. This can be done using, for example, first token embedding, the last one. We can do some poolings, mean, max pooling, etc. Somehow we create this embedding, and we put multi-layer perceptron head just to predict our final class. So in practice, interesting that this approach works almost at least the same as the BERT, and sometimes even better than tuning BERT. At least you need less data to do such tuning. Also important to say that when we do such tuning, we do not train the whole model. The whole model stays frozen. We have two options. We either train the head, or we can train the head and some additional parameters. I'll speak about them a little bit later. So it's important to understand that we can afford to train the whole model. It is too expensive for such a task as we solving. And the next idea is to do intent probing. The idea is very simple, almost the same as with intent classification. Sometimes there are such questions in chatbot that we can't answer just at the moment. For example, client can type something like abracadabra, and we don't understand at all what he wants. And in these cases, we need to ask him some question to clarify his intention. So we can generate such questions directly using large language model. And finally, the most interesting part, we can just do answers using large language model. We can try to generate answers for client questions. But if we use naive approach, if we just take, for example, ChatGPT and ask it to answer banking questions, of course, we will run into a problem. The model will start to hallucinate. It will start to imagine some facts, some products, some conditions that are not real. And that's the way the large language model actually works. They are trained to generate some output, and we can do nothing. They just train. So somehow we need to solve this problem. How can we deal with hallucinations? The first idea is to add some knowledge. In every company, there is internal knowledge base. Usually it is a set of documents, a set of articles. Those articles are describing bank products. And the simplest idea is to just concatenate all these documents and put them directly into the prompt. But that won't work because, first of all, context window is usually limited. And by context window, I mean the number of tokens model sees when it generates the next token. Yes, nowadays the context window are getting bigger and bigger, but to support this, we need to use some really large, expensive model that is overkill for real banking application. And even if we somehow put the whole knowledge database into the prompt, it will still not give a good answer because you can treat it like putting a lot of noise inside the prompt. Most of the documents are sure not relevant to the question you've been asked, and the model starts getting confused. Generation quality will be bad. So the better approach is to use retrieval-augmented generation. The idea is to take a client question, turn it into an embedding, so-called vector. Then we take our knowledge base. We split this knowledge base into parts, into small pieces. Those pieces are called chunks. And for each chunk, we also do an embedding. And then we do vector search. For our query, we find the most relevant, the most similar chunks, the most similar parts of knowledge base using those embeddings. And then when we find this most relevant part of knowledge base, we just put them into prompt. There are several tricks how to cook retrieval-augmented generation. Let's speak about them. The first is retriever part, the part when we do search based on our knowledge base. First, what you need to know is you should use pre-trained embedders, for example, BGE, E5, etc. They are specially designed for retrieval. And in practice, even if you take such pre-trained embedder and you take, for example, Roberta that is tuned on your domain, Roberta will still perform worse than this embedded that is actually not pre-trained on your domain. The next thought is also always remember your domain. Banking domain is absolutely sure specific. There are special words, special questions, and general purpose model may not perform out of the box. So we need to fine-tune the embedder on our domain. This also can be done using contrastive learning approach. You need to collect a data set of pairs, a query and corresponding chunk, and you just train the model on these pairs. You also need to think about chunking, about the way you split your knowledge base into parts. There are plenty of approaches how to do this, but the best approach is to use the structure that is already presented in your data. Usually the knowledge base articles are something like HTML, something like Markdown. There is already some structure in these documents. There are some headers, footers, some paragraphs, and it is a good idea to use this structure. You also need to think about the quality of your knowledge base. In practice, mostly all knowledge bases really have bad quality, and it is a good idea to work with this knowledge base, somehow filter it, add some structure in it, maybe rewrite some articles. We can afford to use some human editors, or you can use a large language model to rewrite the articles. The next idea is to use hybrid retrieval methods. BM25 is one of those classical approaches. It's something similar like TF-IDF, a little bit more advanced. There are some additional hyperparameters, but the idea is almost the same. And in practice, this old algorithm like BM25 still works very well in some cases. And it is a good idea to somehow combine BM25 with vector search. For example, you can just concatenate the outputs of those retrieve algorithms, or you can somehow put weights for BM25, retrieved chunks, and for vector search chunks. And the last thing is two-stage retrieval part. This idea comes from recommender systems, from search, from re-ranking. When you do vector search, usually you calculate something like cosine similarity between vectors, and you can do this relatively fast. And there are some more advanced approaches, for example, cross-encoders, when you put at the same time query and chunk. And this cross-encoder predicts you the similarity. Of course, because the model takes as an input both query and chunk, you need to do a lot of calculations. For example, for one query and 100 of chunks, you need to do 100 forward passes. You can't afford to do this for all your knowledge base, but you can do two-stage retrieve approach. At the first stage, you generate a short list of candidates using simple embeddings with, for example, cosine similarity. And on the second stage, you do re-ranking with cross-encoder. Now let's talk about generation step. Generation step is also important, not so important as retrieval part, but still. First idea is to use few-shot prompting. Few-shots is very simple thing. You basically show the model the examples and the output you want for those examples. So this help LLM to generate a little bit better. You show it the pattern to mimic. Then there are simple, straightforward ways how to control hallucinations directly with hyperparameters. For example, you can put a low temperature, and you can do this directly via prompt. You can just ask model to do not invent an answer, say that the answer is not found if it's not found, and that helps. Next is chain of thought. Also simple idea, you just ask model to reason through the retrieved chunks to do step-by-step thinking, and this makes model behavior more predictable. The next idea is to use structured output. It's also a way to somehow control the way model generates. You add some limitations on the possible generated output. For example, you can force it to do generation in JSON format. You can ask it to generate answer, use chunks, reasoning. And when you do such things, for example, when you do code generation, there are some rules on the possible tokens. For example, you can't start the generation with closing bracket. You should start only with opening bracket, and so on. So there are special libraries. For example, one of them is just called structured output when you work with such generation. Next is to use system prompt. System prompt is a special prompt that sets the tone and behavior through the whole session. You just ask model to be an assistant in one prompt, and the whole next dialogue, the model will listen to this instruction. So we can just directly say you're an assistant for a major bank, you need to help customers, you need to provide accurate, concise answers, etc., etc. Now let's talk about metrics. In practice, metrics really matter. And when we deal with RAG pipelines, they are complex. There are a lot of components, a lot of hyperparameters, and that's why there are multiple layers of metrics we need to talk about. First of all, when we start with the retriever performs re-ranking task, so we can take some metrics from recommender systems. We can take some simple metrics like hit as k, whether at least one relevant chunk appears in top k results. We can use something like MRR, mean reciprocal rank. Basically, we just take the position of the relevant chunk in our output, so-called rank. We do invert of this rank, and we calculate the mean over the whole set. But it is important to understand that those metrics, our true goal is different. When we speak about retrieval-augmented generation, we want to be sure that whole context, whole retrieved chunks are sufficient enough to generate the output. We speak about so-called context efficiency, and this is a higher level metric. It's hard to calculate such metric automatically or mathematically, we need to do human evaluation. We just need humans to evaluate such metrics. Or we can use LLM as judge. We can give LLM the same instruction we give to humans. But when we do with LLM as judge, we need to be careful because this approach needs calibration. You need to be sure that your scores from LLM and your scores from humans are at least correlated. So maybe it's a good idea to do human eval first and then try to tune your LLM as judge pipeline on these human marks. Okay, let's move on to the generator part. Generator metrics, the most important and the most key metric is business metric. The whole things we do is to make business metrics better. That's why we need to focus mainly about those business metrics. For example, automated dialogues, client feedback. The problem with business metrics is they are high level. You definitely can't calculate them in offline. The only true way to evaluate business metrics is to do A/B testing when you split your clients. For one group, you show one dialogue system, for the other, you show another. And of course, we can't run A/B tests for every small change in the pipeline, for every hyperparameter change. And we need some other metrics for those cases. There are such metrics like faithfulness. Faithfulness tell us about how answer based on the provided context. We want model to be grounded with the knowledge we provided to it. So we just need to evaluate is the answer based on the context. Next metric is the answer accurate? Correctness. We treat our knowledge base as ground truth information, and we want the answers to be corresponded with this knowledge base. We want the answers to be correct. By correctness, we mean our knowledge base. Next metric is relevancy. We want answer to be relevant to question. You can imagine cases where the answer is okay, it is correct, it is faithful, but it is answer for another question, not for the one the client came to chatbot. And these three metrics are also such high-level metrics. We need to do human evaluation to somehow evaluate such metrics. There are some proxy metrics we can calculate in offline. To do so, we need a reference dataset of golden answers, and then we can calculate blue, something like precision, rouge, something like recall, meteor, something like F1 score plus synonyms and order. But again, when we speak about such proxy metrics, we need to be sure that they are correlated with human evaluated metrics. Okay, let's talk about advanced RAG approaches. The first thing we can do is to make advanced retrieve path. First idea is to rewrite queries. The problem is that queries or client questions, they are maybe too short, they may be informal. There is domain gap between client questions and our knowledge base. And we want to somehow make this gap less. So to do so, we can try to rewrite our queries to be more formal so that queries are more corresponding with information in knowledge base. Another idea is to do hypothetical document embeddings. The problem is the same. The domain of questions and domain of possible answers in knowledge base are different domains, and we generate some possible LLM answer, and we do retrieval using this LLM answer, not the query, and our knowledge base. And we can do something with generator part. Mainly, we can do fine-tuning. To do so, we need to collect ground truth golden answers, and we can try to somehow do lightweight fine-tuning. Sorry. Those approaches are called parameter efficient fine-tuning. There are plenty of them, but the key one are prompt tuning and LoRa. Prompt tuning is basically when you have your input text on the embedding level after tokenization, you add some additional embeddings, so-called tunable soft prompt, and you change only those additional embeddings. The whole other model stays frozen, so there are very little amount of parameters, but you can still somehow change the way the model generates its output. And LoRa, as you know, there are a lot of linear layers in LLMs. There are multi-layer perceptrons in every block. There are key value query transformations that are also linear. So the idea is to add some low rank metrics initialized by zeros. We do so using two matrices in practice. One is from D dimension to R, the second from R to D. And we tune only this additional matrix. R should be smaller than D, and the whole base model weight, pre-train weight stays frozen. Okay, let's speak about limits. There are some limits when we speak about knowledge base. Not all questions can be answered using only knowledge base. For example, client might ask something about his personal information. He can ask something about his yesterday transaction. And of course, there is no information about client's transaction in our knowledge base. It is personal information, it is online information, and it is not presented in knowledge base. So we need to do retrieval augmented generation based on client data. Or client can even ask us to do some actions. He can ask us to block his card, for example, and it means that our large language model somehow needs to perform an action, and this is the place where agents come in. Nowadays, everybody is talking about agents, but in practice, I haven't seen agent that works in real production environments in such regulated sphere like fintech, like banking. There are some inference limits. When we speak about banking, first of all, we can't use LLM via API because of client personal data. So we need to host LLM inside the bank. We also need to remember that LLM can generate an appropriate response. For example, it can generate something bad that we can't show to our clients, and we need to do pre and post processing somehow to detect those cases when the answer is inappropriate. And we also need to remember about economy. The cost of the inference should be lower than human operator. Otherwise, there is no sense in doing such automation. So we need to use small large language models, and we need to do fast inference. A few words about fast inference. In practice, there is a place for the whole lecture on this topic, but I'll say the basic ideas. First, you need to know that there are great tools that already done, for example, LLM, that already include all this stuff. And let's check what's inside. First is batching. Batching is basically just combining requests together to one batch. As you know, GPUs are performing better when we speak about batches. So we just combine multiple requests and put it together in the GPU. The next thing is key caching, that is key value caching. As you know, LLMs are generative models. They are doing autoregressive generation token by token. And at the next step, when we generate next token, we need to calculate the query to key similarity between all the previous tokens. Then we need to take all values from the previous tokens. And we do not want to calculate keys and values for all previous tokens every time on every step. That's why we do caching. We just save those keys and values. There are some advanced techniques about attention. Page attention, flash attention, they usually works with memory access patterns, and they are already implemented when we speak about VLLM. Another big thing is quantization. We can reduce the size of the weights. For example, we can use not floating point 32, but something like int4. So there is less bits, less bytes for one weight, and the model become much faster. And the simple idea is to use multi-GPU inference when you try to generate in parallel using several GPUs at the same time. And there are some ideas about caching. First idea is full response cache. It means that when we receive the same query we've seen before, almost the same, like comparing texts, we can just return the previous generated response, so we don't need to generate the same answer. This almost the same idea about similarity-based caching. If we see a query that is similar to the query we've seen before, we just can take the generation for this seen before query and skip the generation part. And prompt level caching. Usually in prompts, there are some parts that are fixed, that are not changing between the generations, and we can just cache those parts separately. We can cache queries for them, keys for them, values for them, so we don't need to calculate them for each new generation. Okay, let's return to our customer journey. Imagine our dialogue system fails. We fail to answer to client. In this moment, dialogue transfers to operator, to human, and operator has some UI. Via this UI, operator communicates with client. There is some place where operator can type his answer. There are some buttons, for example, viewing client data, viewing transaction history, active products, etc. And of course, in this UI, there is place we can try to put some models to help operator reply faster. We want to assist operator. We want them to work faster, so our clients receive the responses faster. We are coming to the idea of ML-based operator assistant. First thing is shortcut to relevant place in interface. For example, these buttons we have like client data, transactions, history, and so on. There are plenty of them, and we just can show the most relevant place in the interface for this dialogue. Training this model is rather simple. We need to collect a data set, dialogue, and corresponding place in the UI. We just need to log the UI clicks from our operator and do multi-class classification training. In practice, we have little data in this case, so old approaches with LSTM and FastText works even better than BERT. Next thing is response template. We want to show some template for operator so he can just copy and paste this template. For example, there are some things like your card has been blocked, we've submitted your request, etc., etc. And we want to recommend these templates automatically. From the machine learning point of view, there is an embedder. We just take BERT, we do mask language modeling pre-training on the dialogues. Then we do pre-trained stage. We do contrastive learning on pairs, dialogue, and operator response. And we do fine-tune stage, contrastive learning on pairs, dialogue, and response template. So our model predicts the most closest, in case of embedding vectors, the most closest template for the current dialogue. Next thing is LLM-based operator assistant. We can just show the possible answer to the client question during the dialogue. Under the hood, it is retrieval-augmented generation again, and answer will be validated by operator. So if operator checked the answer, if he's okay with it, he just press send and LLM answers transfers to our client. And last thing is message enhancer. In practice, operators usually write not so well grammarly structured texts. So we want to fix that. We can add some button that corrects grammar, corrects spelling, adjust tone, style, and make message more clear, easy to understand. And under the hood, again, it can be done with a large language model. Basic approach just with prompting. In more advanced approach, we can fine-tune LLM for this exact problem. Okay, imagine operator solved the problem. The dialogue is over for the client, but for the operator, the job is not over yet. Operator needs to log information about dialogue because bank wants to understand the distribution of communications, what products client asks, what problems there are, what channels are used, and so on. In practice, there is really sophisticated structure of classes. It is hierarchical classification. We have product. For each product, we have subproducts. For each product, we have also topics and subtopics. And there can be more than 600 of classes for subtopic, for example. So we have a lot of classes, and we have a complex hierarchy of classes. How can we solve this? Naive solution is to take historical labels from operators. We know that operators do such logging. We just take those labels they put, and we collect such data sets of pairs, dialogue, and historical label. As a model, we take BERT. We put 6 heads because we have 6 classes, and we do training. In practice, result is poor, 47% for subtopic classification. And the reason is simple. Operators just lack time to deal with already finished dialogue. They want to skip to the next dialogue. That's why they pay not so much attention in putting right labels. So we can't train good model using these historical labels. Then solution is we need to collect a data set that is good labeled by specialized human assessors, by human data labelers, and we receive a quality like 77% for subtopic, which is better than the quality that operator did. Okay, there are in fact plenty other LM cases. In every corner of the bank, there is someone who is trying to do an assistant, to do agent. Someone tries to do data labeling with LLM. There are LLM for technical support. A huge part is about code generation, about reviewing code, about generating code. There are some tasks about media screening when you take news and you want to extract some information from this news using large language models. But basically, under the hood, the approaches are the same I spoke about. LLM, use LLM, use retrieval-augmented generation, do fine-tuning, and do all these little tricks. That's it. Thank you. Feel free to write. And by the way, we are hiring. I have several open positions right now, so you can send your CV if you are interested.
Hello, thank you for presentation. What actually do you use to accelerate inference of LLM? You enumerate some list of methods, but what actually you do?
this one. Yeah, in practice, we do almost all of these things. First of all, we use VLLM because VLLM just a great tool that already has implemented all this stuff. And we try to do caching. We already have full response caching, similarity query cache in work, and actually prompt cache is also done in VLLM. So it should be in the left box. In fact, no, sorry. I think that's almost all. We also use small large language models, less than 10 billion parameters, because they work fast. And when we add such things, we can afford to do such generation on high requests per second.
Thank you for your presentation. While we inference large language model with a lot of parallel users, KV cache a lot of memory that the model is needed is KV cache. Do you use KV quantization?
Okay, I see. So when we speak about KV caching, of course, there is some trade-off between the speed of generation and the amount of memory we need to store. But when we combine KV caching with page attention, the problem is a little bit smaller. And in practice, we do not go deep into such tools. We do not code them by ourselves. We just use already done open source things like VLLM, where this implemented. So we are not doing something like that.
Some open source libraries support KV quantization. For example, we can store KV cache in QH.
Okay, I guess we need to check if this KV cache quantization is in VLLM.
Okay, thank you.
Thank you for the presentation. What are the most widespread methods for model compression in industry?
Methods for model compression in industry.
Yes, in industrial applications.
So as I said, actually this slide is the things we use. So I do not do some research about the whole industry, but you basically do
GPU experience.
Yes, you basically do quantization. You try to do multi-GPU inference. You take a model with less amount of parameters, because for such problems that we face, you don't need to use 70B model, and that's already enough.
If there are particularly useful articles for the methods for model compression, could you please send it?
Okay, I'll check, but as I said, we are not doing research. We are doing applied things for business.
There are some really
Okay.
approaches. Thank you.
Hello, name is Roman. Thank you for your lecture. Basically, I have a question. Number one is what kind of size of models are you usually use for this kind of tasks? It's the first question.
Okay. For the task of tuning the model to solve classification problem, for example, we can use even less than billion parameters. For the task of generation something, we are in practice using models like 8, 9 billion of parameters.
And the second question, have you ever used the tools to determine the inference of the models? I mean, something like maybe you heard about it, guidance AI language or library. Have you heard about it?
Sorry, the tools for what?
To determine the inference, it's just makes the, I mean, the inference
I get.
generation a little bit determinant.
I get the problem. We don't face such problem that we have different generation, and it is crucial for us. So the setting 0 temperature is actually enough for our tasks. There is no problem if we generate different outputs, but both of them are relevant and correct. So we don't need to try to force model to be deterministic.
Mm-hmm. Okay, and the last question is second. I wanted to ask about the strategies for the data chunking, because usually you have really huge amount of answers data, and what do you prefer in these kind of tasks?
Yes, I said about it. So in our case, we have already structure in knowledge base. For example, as far as I remember, we are using HTML pages, and there is already structure in HTML. There are footers, headers, different splitters, and usually this stuff is actually a good thing how to you can split chunks. So you don't need to invent something like splitting by tokens with intersections, etc. You do splitting using this structure that's already presented in the knowledge base. There are some advanced approach when you can use LLM to split into chunks. In my opinion, that's the best possible variant, but we don't need it.
Okay, thank you. And have you ever worked with the structured table data, maybe?
That's a good question. With table data, yes. Again, you can transform your table data into Markdown, for example, and the model starts to operate with them really good. The more complicated question is about images, for example. And in practice, there are a lot of schemes, some information, textual information that are in image, or there can be PDF files. And this is a more sophisticated problem. We haven't solved it yet.
Got it. Thank you. And the last one, I guess it's the last one again about the preprocessing of the data. Second. I guess that's it. That's all. Thank you.
Okay, you can ask me later if you want.
Yeah, I think I remember it.
Okay, we have some questions from Zoom. Could you please answer these questions? What is low temperature means in the context of prompt generation?
Sorry,
It was in the
hard
slide.
to hear. Low temperature.
What is low temperature means in the context of a prompt generation? It was in the slide.
Oh, okay. I mean, not prompt generation. I mean the generation step. And when you do generation, there are some hyperparameters in large language model. One of those is temperature. Temperature is basically in your softmax, there is T in denominator, and you can do lower temperature and higher temperature. If you have high temperature, your output is more chaotic and undeterministic. And if you do low temperature, then your output is more deterministic. That's it.
Okay, thank you. Second question from online. Could you please tell briefly how agents are implemented in LLM chatbots when users send query with action, like block my card?
Если бы я сам знал. Okay, so as I said, in my opinion, agents is good thing. Everybody is trying to do agents, but they are not working actually in production. The idea is, okay, you ask a large language model to do some action, for example, to block the card. And then your large language model, it makes some plan how to achieve this target. And to achieve this target, it may use different tools. For example, it can go to your database, it can push some buttons, and to do such loop, it puts a set of steps. After each step, it can do some tool call. You show it the output of the tool call, and it produces the next step, plans the next action. So this is basically the idea of agents.
Okay, thank you very much. A brief comment that we will talk much more about generation hyperparameters in tomorrow's seminar. So if you are very fan of large language model, you can connect to us in 5 o'clock.
There was one question somewhere there.
Offline questions? Yeah.
Thank you. How do you handle the situation with localization on Russian?
Situation, sorry.
Well, usually we use some pre-trained LLMs, right?
Mhm.
And they are not pre-trained in Russia. Well, not very well, at least the small-sized LLMs,
Okay.
like 1B to 3B. And usually we
Okay, I guess I get the problem.
Yes.
In fact, if you take a large language model, even 1 billion or 9 billion, 8 billion, yes, it is not tuned to work with Russian language, but the amount of data that presented in pre-trained stage is really huge, and there is really huge part of Russian texts in it. So it out of the box understands Russian really well.
Yes, it does understand, but sometimes it's started randomly by
Generating some Chinese text.
Chinese. sounds.
Yes, it can happen if you use Qwen, things like. So I think the most straightforward approach is just to do some regular expression to detect those cases when your model starts to generate something from other languages. In fact, I said that we have pre-processing stage and post-processing stage. It means that we in practice are developing a so-called model of post-processing that detects all negative cases. For example, when model generates something bad, some violence language, all possible risk cases that are bad for bank. And one case is exactly, as you said, when model generates something in English or in Chinese.
So you do monitor.
Yes, this is just post-processing stage. We just classify those cases.
Okay. And also, and last question. So you have a RAG, right?
Yes.
And there is some retriever model. And this retriever model like takes some query and a lot of responses and outputs a score.
Yes.
How do you filter out irrelevant responses?
Sorry, how do
you filter out irrelevant responses? Like by some threshold? Or
Yes, very simple.
Yes,
Just put some
but-
threshold.
By using threshold, you have
Yes, we can show some irrelevant chunks in context to the model. Yes, that's the problem. We can do some adaptive chunk retrieval, so we retrieve only adaptive amounts of relevant chunks. But in practice, we do fixed amount of chunks. For example, that's hyperparameter. We take, for example, 5 chunks every time and put it in the prompt. And in practice, it works well. So model understands which chunks are relevant to the question, which is not. And usually it uses information only from the relevant chunks.
Okay, thank you.
Thank you for your presentation. Yes, a bit provocative question. If I will build AI team Alfa-Bank, Google give me article about AI team in Alfa-Bank. It's article mainly about agents and application of agents in writing Java tests or something like that. Can you tell us something about it, and is it still working and working good? Have you some experience with interaction with these agents, and do they
Okay, I get the question.
errors or something
See, um, Alfa-Bank is big company. There are different teams, and some teams are showing something to the public about agents. But I personally haven't seen agent in Alfa-Bank that works at least in development stage. More than that, I haven't seen an agent in the whole Russian banks that works in production. Everybody is talking about that. Some banks are publishing PDFs, 200 pages about agents, but when you ask employees from this bank, they'll say that no, they're not in production.
Thank you for your lecture. I have also a question about agents. You said like agents are working poorly for your task.
I haven't said that they were.
No, you haven't said it, but
I think it's a great idea, but not just
yeah,
at the moment.
just for now.
Yes.
Yeah. And you also address like a problem of blocking a card, so that agent probably for now won't be able to perform this task. But why not hard code some frequent problems? For instance, like hard code blocking a card number with some high threshold. So if model understand that you need to block a card, so you can so it can be done because it's hard coded like somewhere.
That's
Thank you.
Great idea. In practice, we do this. We have our rule-based chatbot with intent classifier, and for some intents, there are already written scripts that call these systems. For example, I don't know if we blocking card automatically, maybe, but there are definitely such cases. So, and about agents, the problem with agents is that it's hard to imagine that business allows us to give access to the whole operator interface so that agent can act there. They will ask us who is responsible for the bad decisions, for example. This is the main problem when you speak about agents in regulated environments like banking.
Thank you.
Okay. Thank you very much. Oh, we have one last question from the chat. We have a lot of problems because model, even large model, talks in the not normal Russian, like джинсы is джинсы. What do you do with it? Do you have such problems, and what do you do with that?
Джинсы is джинсы. I can suggest to try different large language models. It's actually a hyperparameter. What model you can use? There are plenty of them. Great tools. Most of them are open source. Some are not, but you are not forced to use this exact LLM that generates something strange.
Okay. Thank you very much. It was the last question.
Thank you.
Okay.